Okie dokie, so today we're talking about the Calvin cycle in a bit more depth. Really, this is going to be about, since I covered it in general, um, I want to talk about how tracking the carbons as it goes around. It's kind of making sure that I can show that no carbons are made or destroyed in the Calvin cycle. Cool. So it's really weird because it's a cycle, and we don't put in the full amount of stuff that's used each time because stuff is reused. So I'm going to start with RuBPH. This is a 5-carbon molecule, and then CO2 is a 1-carbon molecule. So I'm going to keep this. So we have RuBP. We have, and this is a 5-carbon molecule, or no, this is a 5-carbon molecule. We have CO2. This is a 1-carbon molecule. Cool. We have also PGA. PGA. This is a 3-carbon molecule. We have PGAL, or G3P. PGAL. And this is, once again, a 3-carbon molecule. And then anything else that I'm missing? No, that looks all good. Cool. And so then in the reaction, see, I put in 3 CO2s. So if I put in 3 CO2s, and I have 5 Rubiscos, oh no, I have 3 RuBPHs, excuse me. Rubisco is the enzyme that RuBPH is going to go through with CO2 to make the to get from here to here. That's where we get from here to here. That's where Rubisco goes. So in here, I'm going to take my RuBPH is 5 carbons, so I have a total of 15 carbons. And then for my CO2s, I have a total of 3. Oh, I started the 3 backwards. 3 carbons. So because PGA is a 3-carbon molecule, and this equals 18 carbons, I'm going to have a total of 18 carbons. And it's true that PGA has a 6-carbon molecule. So 6 of the molecules times 3 carbons each molecule is 18 carbons. Okay, so we haven't lost any carbons. We have a total of 18 carbons in the cycle when we're here. So then it goes through these reactions. 6 ATP is put in, 6 NADPH is put in, and we get to PGAL, or G3P. We still have 6 of them, and we have 3 carbons per molecule. And so that's going to give us a total of 18 carbons. So we still have our 18 carbons, but this is where the carbon number changes. And we're going to get an offloading. 1 G3P, or PGAL, leaves. So that since one of them is a 3-carbon molecule, we subtract 3 carbons because one of them is going to leave. So now we have 5 G3P molecules. I'm just going to stick with G3P because it's faster to write, which times a 3-carbon molecule equals 15 carbons. And so now I have 15 carbons, and that's going to do stuff. Spend 3 more ATP to get it back to RuBP, which is our 5-carbon molecule. So it's a 5-carbon molecule, and I have 3 of those, which equals 15 carbons. And then I'm going to add back my 3 CO2, and I basically start the cycle. Again, kind of going through this process. So so we leave 1 G3P and it comes out, right? So this 1 G3P is a 3-carbon molecule. But to make glucose, we need 6 carbons, right? Because it's C6H12O6. So we need 6 carbons. So we have to do the cycle twice to get our 6 carbons to make 1 glucose. And so when we do that, we're going to take the total 9 ATP used, see, 3 and 6 ATP, and the 6 NADPH, and the 3 CO2s that we put in, because like we didn't put in PGAL and RG3P and PGA, and these don't come out, they just kind of stay, and so these, the 15 carbons will rotate through as one is pulled out. But we got to do it twice, so we got to multiply everything here by 2, and so that's going to give us 18 ATP 12 NADPH, and 6 CO2s used. And so that's how we get 18 ATP. That's where it comes from, or that's where it's used in the Calvin cycle, where it comes from the light-dependent reactions, and the same with the NADPH. And then the CO2 is diffused in as well. But that's how we get to 6 CO2, and I hope that was helpful.